Alright, here's a problem, calculus problem. We want the volume of an object, and for once, so far we've done only objects of revolution, and we'll do some other examples, but here's one where we really don't know much about the shape of the object, and it's not assumed to be a volume of revolution. Maybe it's something that looks something like this. Some sort of blob. I've got a sort of a teardrop shape, and I'm imagining, it doesn't really look like a dinosaur bone, but I'm imagining it maybe this is a fossil dinosaur bone. And it's not going to get smaller. And what we've done is, or somebody else has done, is they have looked at slices of this. Maybe they didn't actually slice it up. They didn't destructively do this, but they've figured out. They've sliced it in regular slices from the left to the right, which I'm kind of suggesting with the circles here, although I didn't make them very regular. It wasn't that easy to do in Paint, unfortunately. And they sliced them with slices of thickness 1.5 centimeters, and they recorded the cross-sectional area of each slice. So right at the end, there's no cross-sectional area. Then the next one, they've got 3.5, then 4.2, 5.4, and then it gets down to 0 again at the end. Now, it doesn't have to start and stop at 0. It could actually have like a circular cross-section at the end and actually be sliced off. But if it's a rounded shape like this, it's actually not that unreasonable to start and stop with 0. And what they're asking us is simply what the volume is for this thing. And what's nice about this is how simple this kind of problem is. People tend to overcomplicate it. We know that the basic idea is the volume is the sum of the little bits of volume. And each little bit of volume is, if I'm slicing it, it's still a of x dx integrated. And we've had situations where we could algebraically calculate a of x. This is like a pi r squared or a washer or something like that. But what if that's actually just given to us in the data? We don't have to go any further than this to use this data. We're not going to put any pi's in here because there's no these aren't necessarily circular cross sections. We're not talking about r's. This is not giving the radius. This is actually calculating the area. They've done most of the work for us by calculating these cross-sectional areas. We just have to add them up. And of course, that's approximately equal to the sum of a of x delta x. And that's, of course, approximately equal to a trapezoid approximation or a midpoint approximation. And I'm going to show both of those because I like having people do both of those each time we do this. Okay, so the trapezoid approximation, well, delta x, what's the delta x? Oh, there it is. It's the thickness. We've got a cross-section of 3.5 square centimeters. Multiply that by the thickness 1.5 centimeters, you've got the volume of one of these slabs. You want to imagine like a slab from here to here, right in here, between these two kind of vaguely circular things. And you want to think of that as the dV of the volume. That's just the cross-sectional area times the thickness, and the dx is just a little bit of thickness going like from here to here. Okay, that's going to be the dx. So, well, really a delta x, because it's not a dx. dx is the infinitesimal version where we can do everything with a fundamental theorem. Here it's really demoted back down to a delta x. Okay, but we know the formula for that. It's delta x times, and the way I like to do it is I like to take the first and the last separately and say just take the average of the first and last. So I'll call these A1 through A0 through A1, 2, 3, 4, 5, 6. Okay. So area of the first one plus area of the last, the sixth one over 2. Now that's actually going to be 0. Plus A1 plus A2 plus A3 plus, oops, A4 plus A5. And so it's just the regular idea of sum of the height. Well, it's not the height anymore, it's the area. But this is the height if I tabulated this function and graphed this function. And we're really just integrating that guy. We're integrating cross-sectional area times dx. And so it's just the usual idea with these guys demoted to half strength and averaged. Okay, and so what that ends up doing is it's just going to be the 1.5 times the sum of all these guys. Very, very simple. plus 2.3, and that's equal to 27.9. And for some reason it doesn't like to put that inside a display, and we're good. Okay, what about the midpoint? Probably won't give us exactly the same answer. Remember, the midpoint is only convenient to use if I have an even number of intervals. For tabular, midpoint is not that great. So this is, we've got A0 to A2, A2 to A4, A4 to A6. Okay, so we're really going to use a delta x that's twice as big, and then these, the 3.5, the 5.4, and the 2.3 are going to be the middle of those guys. So here the delta x has been changed to 3 centimeters. And so let's put this T, this is T6. This is going to be M3, because we can't access M6, unfortunately. So that's going to be 3 times, and then we just take only 3 of these data points, 3.5, 5.4, and 2.3. And we've seen that really for tabular data, the trapezoid rule is really better. But it's nice to know what the midpoint rule will give us. 33.6, actually significantly different. Okay. And so that's the new delta x for the bigger intervals times the midpoints of those intervals, and we're only using some of the data that we had from the other one, the trapezoid rule. And so the main thing I wanted to get across here is don't overcomplicate it. You've got these first 3 steps, and then none of the rest of the story has any relevance, the pi r squared and all that kind of stuff. We're ready to go. We just take this data and integrate it. And because these are areas, when you integrate those guys, they give you a volume automatically.